I don't know. Stavros. Christine. No, the other Christine. Your cousin, you know, the one who's been working generously all night for your architecture presentation? Right. Well, it's going okay. I've just put all the images into the sequencer in the computer, and now I'm working on the kiosk itself, but I need to know, how big is this TV screen going to be? Well, I need to know because I have to cut out the hole to make it fit. Oh, 21 inches, okay. But that's diagonally, right? Well, what's the length and the width? Well, just go measure it. What do you mean the TV's not there? No, I can't ask Kanwal. He's in Montreal at a math conference. He's not going to be back till tomorrow morning. All right, well, I'll figure out something, don't worry. Well, it'll be ready by tomorrow, okay? Relax. All right, bye. What's that? Euclid?
No, not Euclid. Pythagoras.
Pythagoras? The ancient Greek mathematician? Are you serious? Get out of here.
You need my help
I do?
to calculate the size of your magic box. Your television.
Oh, great. Well, how big is it?
This you can calculate yourself. But listen, you need to know this. The ratio of height to width of all television screens is 3 to 4. And remember my theorem.
The theorem? Can't you just give me the answer right now?
You're lucky I told you this much. You should have named your computer after me. Farewell, and good luck.
Pythagoras.
Hey, bonjour, mon ami. Well, you look bright and ready to do a show.
I guess I must have fallen asleep.
Uh-huh.
Oh, hi, Kanwal.
Hi.
Nice sweater.
Thanks.
Oh, and you know what?
What?
I had this dream that Pythagoras came and... Ooh, maybe it wasn't a dream.
You mean you had a visit from Pythagoras from 500 BC?
Well, in a dream, yeah, but at least I think it was a dream. Anyway, I have to figure out the measurement of the length and width of a television screen, and I have to cut a hole to make sure it fits in here, but I only know the diagonal measurement. Anyway, Pythagoras said that I could use his theorem in a ratio of 3 to 4.
You know, there is no arguing with Pythagoras. He's right in both cases.
Really?
Yeah.
Oh, it's late. Oh, hi, math fans. You're watching Math Shop, where we do math round the clock and even in our sleep. I'm Christine, and this is my colleague and world-class math coach, Kanwal.
Hello.
And this efficient pile of hardware over here is my homemade computer, Euclid. Anyway, on today's program, we'll show you how to solve problems involving radicals. You'll learn about entire radicals, mixed radicals, and how to perform operations on expressions with radicals in them.
First of all, we can use radicals to solve this television screen question. I know from the Pythagorean theorem that in a right triangle with one angle equal to 90 degrees, the following is true. The length of side A squared plus the length of side B squared is equal to side C squared. Now, C is called the hypotenuse. It's the side opposite the right angle, or 90 degrees. This applies to any right triangle. Euclid? If I draw a diagonal across a television screen, I form two identical right triangles. I can label the sides of one triangle A, B, and C. The Pythagorean theorem applies here too. So now, let's substitute what we know into the diagram. We know the diagonal is 21 inches. We also know that the ratio of the sides of the screen is 3 to 4. This means that we can represent the length of these sides using a variable x. So a is 3x and b is 4x. If I substitute these values of a equals 3x and b equals 4x into the Pythagorean theorem, I get 3x squared plus 4x squared equals 21 squared. While 3x squared is equal to 9x squared plus 4x squared is equal to 16x squared, and 21 squared is 441. I combine the like terms, which gives me 25x squared is equal to 441. To isolate the variable in one side of the equation, I divide both sides of the equation by 25 to get x squared is equal to 441 divided by 25. To proceed from this point, we have to find the square root of some number, which is an example of a radical. So we'll hold on to this problem and come back to it later after we've learned a little about radicals.
To understand radical expressions, it helps to be familiar with the way we write them. Euclid? This mathematical symbol is referred to as a radical. The word radical comes from the Latin term radicalis, meaning root. This symbol is possibly derived from the letter R, which again stands for root. It identifies the root of a number, sometimes called the square root or the principal root, terms we use interchangeably. The number evaluated in a radical expression is called the radicand. For example, the square root of 9 is 3. 3 is the root, and 9 is the radicand. The root of 144 is 12. 144 is the radicand, and 12 is the root.
The square root of a number is actually the opposite of the square of a number. For example, the square root of 9 is 3, and 3 squared is 3 times 3, which is equal to 9. In the same way, 12 is the square root of 144, and 12 squared is 12 times 12, which is 144. So far, we've been looking at numbers that have square roots, which are whole numbers. These are a special set of numbers which we call perfect squares. Any radicand that has a whole number as its root is called a perfect square. The radical symbol is not only used to identify the square root, it can also indicate the cubed root or the fourth root or any root for that matter by adding a number in this location of the radical symbol. Now this number is called the index. Whenever you see a radical with no number in this spot, it is assumed to be 2. So the radical symbol means by default that this index is 2, not 1. Here are some examples. The square root of 16 is 4. 4 times 4 is equal to 16. The third root of 512 is 8, sometimes also called the cube root. 8 times 8 times 8 is 512. In other words, it is the number 8 used as a factor 3 times. Now, for the rest of the program, we will be focusing on the square root.
But Kanwal, as far as square roots go, you've only given us half the picture. Not that I mean to be negative or anything.
Negative? Oh, right, negative. That's a very important point to remember about square roots. There are actually 2 different numbers that can be used as a factor twice to get the square root of 16. The question is, which one? They are 4 or negative 4. Now, a negative number times a negative number also gives a positive number as a result. If x squared is equal to 16, then x equals positive root of 16 or negative root of 16. So, x could equal 4 or negative 4. Now, let's take a look at our next point, which is the entire radical. Now, these are all entire radicals. Root 2, root 18, the cube root of 97, the fifth root of 55. An entire radical is any radical which has a coefficient of 1. An entire radical is important because it can sometimes be factored or simplified, much like polynomials. You can often factor an entire radical into a series of smaller radicals, some of which may be perfect squares. Perfect squares can be converted into whole numbers, which are a lot easier to deal with. So, factoring is an important technique to have when dealing with radicals. Well, let's do a couple of examples. The square root of 18 is an entire radical because it has a coefficient of 1. Now, 18 is not a perfect square, but it can be factored. The factors of 18 other than 1 and 18 are 9 times 2 and 3 times 6. Now, of these factors, only 9 is a perfect square. So I can rewrite the radical this way. Radical 18 is equal to radical 9 times 2. Or I can break it off into this, radical 9 times radical 2. Now, the square root of 9 is 3, so my final answer is 3 root 2. 3 root 2 is now a radical with a coefficient not equal to 1. So it is referred to as a mixed radical.
At times, it may be useful to convert mixed radicals back to entire radicals. You can do this by working the process backward.
For example, 5 root 2 is a mixed radical. To convert to an entire radical, I square the coefficient and place the result under a radical symbol. This gives me root 25 times root 2. Now, the product of these two radicals is root 50. Now, which is an entire radical? Because the coefficient is 1.
To do this conversion, we use something called the product rule, which is our next topic. As Kanwal just showed you, whenever you multiply two radicals, you can multiply the numbers under the radical signs. Let's check this out more closely. Okay, Euclid, get radical, dude.
Gnarly. The square root of 9 times the square root of 4 is equal to 3 times 2. 3 times 2 is 6, and 6 is the square root of 36. But 36 is also the product of 9 times 4.
So, the product rule states that the square root of some number a times the square root of some number b is always equal to the square root of a times b.
This product rule also applies to the coefficient of radicals. Let me show you another example. 5 root 9 times 2 root 4 is equal to 5 times 2, 10, 9 times 4, root 36. Now, if I complete the calculation, you will see this is true. 5 times the root of 9 is 3, times 2 times the root of 4 is 2, is equal to 10 times the root of 36, which is 6. Now, 5 times 3 is 15, times 2 is 4, is equal to 10 times 6, 60, 15 times 4, 60, is equal to 60. So, the product rule also states that C root A times D root B is always equal to CD root AB.
The product rule tells you how to multiply radicals, but it is also possible to add and subtract them. Whenever you add or subtract radicals, you must remember that you can only do so with radicals that are alike.
Like this. The square root of 2 and the square root of 3 are unlike terms because the numbers under the radical symbol are different. On the other hand, 7 root 5 and 2 root 5 are like terms because the number under the radical symbol is the same, the number 5. When you have like terms, you can add and subtract them by adding or subtracting their coefficients. So, if I add 4 root 3 and 7 root 3, the result is 11 root 3. Here's another example. 5 root 12 minus 3 root 12. Now, these are like terms because in both cases the radicand is 12. Therefore, we can simply subtract the coefficients to find the solution is 2 root 12. Now, here's the additive rule for adding like radicals. A root c plus b root c is equal to a plus b root c. Now, here's another example, which is a little different. 4 root 12 plus root 27 minus 2 root 50. Now, when I look at it, I do not see any like terms. But is it possible to find like terms through factoring? Yes, it is. Watch. 4 root 12 can be factored to 4 times the root of 4 times 3, plus 27 can be factored to 9 times 3, and 50 can be factored to 25 times 2. Now, I see a number of perfect squares, and if I solve for them, I get 4 times the root of 4 is 2 root 3, plus root of 9 is 3 root 3, minus the root of 25 is 5, so I have 2 times 5 root 2. Next, I do some multiplication, giving me 8 root 3 plus 3 root 3 minus 10 root 2. And now I finally combine the like terms, 8 root 3 plus 3 root 3, which is 11 root 3 minus 10 root 2, which is my final answer.
Kanwal has shown you how to factor radicals and the rules for adding, subtracting, and multiplying them. But what do you do if you encounter a binomial with radicals in it? In such a case, you can use the FOIL method to solve them. Remember, FOIL stands for first, outside, inside, and last, and it helps you to work through binomial multiplication in an orderly way.
And I'll demonstrate. 5 root 7 minus 2 root 3 times root 7 plus 4 root 3. Now here are two binomials. I multiply the first terms, which gives me 5 root 49 outside plus 20 root 21, and inside minus 2 root 21, and last minus 8 root 9. I collect the like terms, and I have 5 root 49 plus 18 root 21 minus 8 root 9. Next, I simplify. I have 5 root 49 is 7 plus 18 root 21 minus 8 times root 9, which is 3. Next, I multiply, which gives me 35 plus 18 root 21 minus 24. Now, I collect the like terms again, and the final answer is 11 plus 18 root 21.
Okay? Let's move on to the kiosk problem now, because I am ready to cut the hole for this screen. But I don't know the dimensions yet.
We're almost ready to do that. We still have one more topic to cover first, and that is dealing with a fraction as part of a radical. Euclid, help us out. If you encounter a fraction all under a radical symbol, the first thing you can do is to separate the numerator from the denominator and place the radical symbols over each one separately. This is called the quotient rule. Let's look at an example. The square root of 4 over 27 can be rewritten as the square root of 4 over the square root of 27. The square root of 4 is 2, and now, using the product rule, I can factor 27, which is 2 all over the square root of 9 times the square root of 3. I see that 9 is a perfect square, so finally, I'm left with 2 over 3 root 3. Here's another example involving division of radicals. 12 root 42 over 4 root 6. Whenever the numerator and denominator have coefficients, you can separate the coefficients from the radicals like this. 12 over 4 times root 42 over root 6. This gives me 12 over 4, 3 times, and according to the quotient rule, root 42 over root 6 is the same as root 42 over 6. Now, if I simplify, I get 3 times root 7. I've been able to eliminate the fractions from the expression. Now let's go back and look at the problem Euclid showed us just a minute ago. He stopped at this point, and this expression still has a radical in the denominator. If we want to eliminate the radical in the denominator, we can do this by applying a technique called rationalizing the denominator. Okay, Euclid, you got this far. 2 over 3 root 3. Now, I can eliminate the radical by multiplying by 1 or root 3 over root 3. Let me show you. This gives me 2 root 3 over 3. Root 3 times root 3 is root 9. If I simplify, I get 2 root 3 over 3 times 3, which is 9. I have eliminated the radical from the denominator. And now I have all the tools I'll need to solve Christine's mysterious kiosk problem. Let's recap where we left off. Euclid? The diagonal of the TV screen was 21 inches. The ratio of the sides of a television set is a standard 3 to 4. So, we let the lengths of the sides equal 3x and 4x. When we substituted these values into the Pythagorean theorem, we got this sequence. And we stopped at this point because the next step requires the use of a radical. Let's apply what we've learned. X squared is equal to 441 over 25. By taking the square root of both sides, I can isolate the variable x and end up with a radical on the right-hand side. I also know that I can place a radical symbol above the numerator and another above the denominator using the quotient rule. So I have 441 over 25. This isolates the perfect squares of 441, which has a root of 21, and the perfect square of 25, which has a root of 5. So, x equals 21 over 5, or 4.2. Now, think, what do we have to do to complete the problem? I hope you're thinking substitution. Let's look at the problem again. Euclid? We know that the width of the screen is 4x and the height is 3x. Now, let's substitute 4.2 back into our original expressions, 3x and 4x, to find each dimension of the cutout. And I find the screen has a height of 12.6 inches and a width of 16.8 inches. So there it is, Christine. Pythagoras was right. With the help of his theorem, you can now cut a hole 12.6 inches by 16.8 inches and be sure it'll fit.
That's great, Kanwal. But there's still one problem.
Now what?
My ruler's metric.
Oh, no problem. We can convert. So the height is 32 centimeters to 1 decimal place. And the width will be 42.7 centimeters to 1 decimal place.
Ooh, that's great. That's going to fit perfect.
Good.
Oh, where's my knife?
This might be a good time to review all the techniques we've introduced today. Euclid? A radical symbol means that we are looking for the root of the number beneath it. Or, in other words, some value which, if squared, will give the radicand. The root of 16 is either positive or negative 4. Radicals can be multiplied following the product rule, which says that root a times root b is equal to root a times b. A mixed radical is one which has a coefficient other than 1. Mixed radicals can also be multiplied following the product rule, which says that c root a times d root b is always equal to cd root ab. The product rule also allows radicals to be factored. For example, root 12 is equal to the root of 4 times 3, which is equal to 2 times root 3.
Radicals could also be added and subtracted, but only if they are like terms. That is, only if they have the same radicand. Once again, Euclid, please. In such a case, the additive rule says a root c plus b root c is equal to a plus b root c. Finally, fractions under radical symbols can be handled according to the quotient rule, which states that the root of a over b is equal to the root of a over the root of b. Using these tools, you can handle any radical expression, just as you would any numeric or algebraic expression. But we've got to go. So thanks for watching Math Shop, and join us next time when we once again prove that math is just part of everyday life.
Yes, even your life. Goodbye.
Bye. Get that mug at the conference?
Yes, I did.
And this neat sweater, too?
No, I've had this for a while.
Maybe next time I should go to the conference and you can stay here all night.
Okay.
I'll get it, don't worry.
Okay.
Math Shop, Christine speaking. Oh, hi, Stavros. It's all done. Yeah. No, really, I got all the dimensions down. It looks beautiful. What? What do you mean you can only get a 14-inch TV? A 14-inch... What? Okay, that's it. You're fired from being my cousin. No, I'm not doing anything more for you. Okay, bye-bye now. 14-inch TV, huh? What am I going to do, glue that back?
We can try, you know.